Let us begin slowly, and let us begin at the beginning. Tonight, or whenever you are listening, we will think carefully about the mathematics behind large language models. We will not rush. We will not assume that understanding must come all at once. Instead, we will move step by step, returning often to the same ideas from slightly different angles, because that is often how mathematics becomes gentle enough to hold in the mind. Large language models may seem at first like engineering systems, or software systems, or products of computer science alone. But underneath them there is a deep mathematical structure. There is discrete mathematics, because language must first be broken into finite pieces. There is linear algebra, because those pieces are represented and transformed in high-dimensional spaces. There is probability, because the model must assign likelihoods to possible continuations. There is information theory, because prediction is connected to uncertainty and compression. And there is calculus and optimization, because the system is trained by gradually improving a huge collection of parameters. So although the surface of a large language model is language, the inner life of the model is mathematical. Let us pause and reflect on that. A person reads a sentence and seems to understand meaning directly. A large language model does not begin that way. It does not begin with meaning in the human sense. It begins with a finite vocabulary, a sequence of discrete elements, a geometric representation in a vector space, and a probabilistic rule for guessing what comes next. From that layered structure, many remarkable behaviors emerge. It is worth repeating that everything begins from a very simple question. Given what has already appeared, what is likely to come next? And then, given the answer to that question, and then the next version of that question, and then the next, an entire paragraph can unfold. This means that behind fluid language there is repeated local prediction. Behind apparent coherence there is mathematical structure. Behind style, tone, and continuation there is a long chain of conditional decisions. So let us now move gently into the first major idea: tokens, sequences, and discrete representations. A language model cannot work directly with raw human language in its full ambiguity and richness. It needs language to be cut into pieces that are manageable for computation. These pieces are called tokens. One can think of a token as a basic computational unit of text. Sometimes a token corresponds to a full word. Sometimes it corresponds to part of a word. Sometimes it is punctuation, a symbol, a space-like unit, or a short common fragment that appears in many places. This is already a mathematical simplification. Human language feels continuous when we listen to it. It flows. But computation prefers discrete units. Computation wants separable objects, countable objects, finite collections, things that can be indexed and manipulated. So a model begins by taking language and turning it into a sequence of tokens. Why not just use words? That is a natural question. The answer is partly practical and partly mathematical. If every possible word were treated as a completely separate basic object, the vocabulary would become unwieldy. Languages contain many rare words, names, inflected forms, invented forms, and misspellings. A purely word-based system would struggle with rare or unseen cases. By allowing subword pieces, the system can build many words from reusable parts. This makes the vocabulary finite and more efficient. So the model chooses a vocabulary. This vocabulary is a finite set of allowable atomic units. Finite is the key word here. The model cannot work with an infinite collection of primitive symbols. It needs a controlled universe. Each token in the vocabulary can be assigned an index, and once it has an index, it becomes something that computation can organize. It is worth repeating: before there are embeddings, before there are probability distributions, before there is training, there is a finite vocabulary. There is a list of allowed pieces. Language is mapped into that list. This step is conceptually important because it reminds us that a large language model does not process language in an unbroken human way. It processes a sequence of discrete symbols chosen from a finite set. Now let us linger on the word sequence. A sequence is not just a bag of items. A sequence is an ordered object. Order matters. If we take the same words and rearrange them, the meaning changes. In mathematics, this means we are not merely studying sets. We are studying ordered tuples, or ordered lists, where position matters intrinsically. This is a subtle but essential point. The sequence structure of language is one of the deepest starting assumptions in many language models. The tokens do not merely exist together. They arrive in an order. One token comes before another. Our model receives not just content, but content arranged across positions. So when our language model sees text, it does not see a paragraph as a cloud of words. It sees the first token, then the second, then the third, and so on. The mathematics of order enters immediately. Let us pause and reflect. Tokens are discrete units. A vocabulary is a finite set of such units. A text becomes a sequence of these units. And a sequence is fundamentally an ordered mathematical object. That may sound simple, but it is the foundation of everything that follows. Now there is a further abstraction. Once a token has been chosen from the vocabulary, one might represent it in the most direct way possible, simply by its index. But an index alone carries no geometry. It does not tell the model that two tokens are similar, or related, or often appear in comparable contexts. An index is just a label. It says this token is number such and such in the vocabulary. But labels do not yet create a rich mathematical space. This leads us to the next essential idea, embeddings. An embedding is a vector representation of a token. That means that instead of treating a token as only a discrete label, we represent it as a point in a high-dimensional vector space. The token becomes a list of numerical coordinates. It is no longer just a name in a vocabulary. It is now a location in a geometric world. Why do this? Because geometry allows similarity, direction, neighborhood, and structure. Geometry allows the system to compare tokens in a richer way than mere equality or inequality. If two tokens are represented by nearby vectors, then the model may treat them as related in some way. If certain directions in the space correspond to particular semantic or syntactic tendencies, then movement through the space can encode changes in use or context. This is a profound shift. We begin with discrete symbolic inputs, but then we move them into continuous space. A word fragment or symbol becomes a point in a large-dimensional numerical universe. And that move is essential. A model that remained forever at the level of pure discrete labels will have very limited flexibility. But once tokens live in vector space, they can participate in linear operations, projections, transformations, and comparisons. This is where linear algebra enters not as an optional embellishment, but as the central language of computation. Let us stay with the embedding idea a little longer. Suppose you imagine each token as receiving its own coordinate description. Some tokens that occur in similar linguistic contexts may end up with similar coordinates. This does not mean that the model understands meaning as a human does. It means that the training process has discovered useful geometric arrangements. Tokens that behave similarly in the data often become nearby or related in the learned space. So the embedding is not just a translation from symbol to number. It is a learned geometric encoding. And meaning, to the extent that the model captures it, is expressed through position and direction in this space. That sentence deserves to be repeated. In large language models, meaning is not stored as a dictionary definition inside the system. Meaning is encoded through geometry. It is reflected in where tokens and internal representations sit in a high-dimensional space, which directions matter, which clusters form, which relationships become computationally useful. Now, one should be careful. This geometry is not simple human meaning. It is statistical meaning, contextual meaning, functional meaning. A token is represented in a way that helps predict surrounding language. So the geometry is shaped by use. It is shaped by distributional behavior. It is shaped by patterns in data. Still, the geometric perspective is powerful. Let us pause and reflect again. We started with discrete tokens in a finite vocabulary. Then we mapped those tokens into vectors. A vector is an ordered list of numbers, and it lives in a vector space. Once tokens become vectors, we can begin to transform them, compare them, combine them, and refine them using the machinery of linear algebra. So now let us move into that machinery more explicitly. Linear algebra is the main computational language of large language models. If tokens are represented by vectors, then the transformations applied to those vectors are typically expressed through matrices and related operations. Vectors, matrices, and linear maps form the backbone of the system. A vector, in the most intuitive sense, is a point or directed quantity in a space with many dimensions. A matrix is a structured array of numbers that defines a transformation from one vector space to another, or from a vector space to itself. When a matrix acts on a vector, it reshapes, mixes, scales, and redistributes the coordinates. This matrix action is everywhere in language models. It is worth repeating that matrix multiplication is one of the main engines of the entire architecture. Again and again, a representation is multiplied by matrices, producing new representations. The system learns which transformations are useful for prediction. The entries of these matrices are parameters. Training adjusts them. In a sense, the model is a vast organized collection of learned linear transformations, interwoven with nonlinear steps that we will discuss later. Let us be gentle here and build intuition. Why is matrix multiplication so central? Because once a token has become a vector, the model must do something with it. It must transform it from a raw lexical representation into a context-sensitive representation. It must extract patterns, combine signals, and produce outputs. Matrix multiplication provides a highly structured and efficient way to perform these transformations across very large spaces. Each multiplication can be thought of as taking the current representation and re-expressing it. Some directions in the space may be emphasized. Others may be suppressed. Some coordinates may be mixed together. The representation changes, but not randomly. It changes according to learned numerical patterns. Now let us consider dimensionality. The dimension of a vector space is, intuitively, the number of independent directions available. If embeddings live in a space of high dimension, then the model has many degrees of freedom in how it can place and manipulate representation. A higher dimensional space can encode richer distinctions, though it also requires more parameters and more data to train effectively. Dimension matters because language is rich. Many different features of use, syntax, style, relation, and context may need room to coexist. High-dimensional spaces provide that room. But dimension alone is not everything. Structure matters too. This brings us to the notion of rank in an intuitive sense. Rank is related to how much independent transformation a matrix can actually perform. A transformation may formally act on a large space but only truly use a smaller number of directions. So rank measures something like effective expressive independence within a linear map. Why might this matter in language models? Because not every transformation uses the full space in an equally rich way. Sometimes useful structure lies near lower dimensional patterns within the larger space. Sometimes models exploit compressible relationships. Sometimes a transformation can be understood as projecting complicated input into a more organized subspace. And this idea of projection is also important. A projection, conceptually, is a way of taking a point in a big space and focusing on part of it, often by keeping certain components and discarding others. In language models, many operations can be understood loosely as extracting certain aspects of a representation while ignoring others. Not all information is equally relevant at all times. Computation often involves selecting what matters for the current purpose. So when we think of matrices in language models, we should not think only of raw arithmetic. We should think of learned changes of viewpoint. Each linear map asks, from this representation, what should be emphasized now? Let us pause and gather the pieces. Discrete tokens become vectors. Vectors live in high-dimensional spaces. Matrices transform these vectors. Dimensionality provides expressive room. Rank and projection help us think about the effective structure of transformations. And all of this is part of the computational language in which large language models operate. Now we move to probability. A language model does not simply transform representations for its own sake. It transforms them in order to assign probabilities to possible next tokens. At the heart of the model is a probabilistic task. Given the sequence so far, what distribution should we place over the next token? This is a central sentence, and it is worth hearing more than once. A language model assigns probabilities to possible continuations. Not just one answer, but a full distribution over the vocabulary. Some next tokens are considered more likely, some less likely. The model does not generally commit immediately to one single continuation as a matter of mathematics. Rather, it builds a probabilistic landscape over possibilities. This is where conditional probability enters. Conditional probability means probability given some information. In this case, the information is the sequence of LLM tokens. We are not asking, in general, how likely a token is in all circumstances. We are asking how likely it is given the context that has already appeared. If the current text strongly suggests a certain grammatical continuation, then the probability of that continuation should rise. If the context narrows the subject matter, then certain words become more plausible. If the text has established a style, tone, or topic, the distribution changes accordingly. So probability is always contextual. It is conditioned on the past sequence. Let us say that again in a slightly different way. The same token can be very likely in one context and very unlikely in another. Therefore, a language model must learn not static word frequencies alone, but context-dependent probabilities. And this context dependence is everything. Now, if the model can assign a conditional probability to the next token, then a longer sequence can be described as a chain of such steps. The probability of an entire sentence or paragraph can be decomposed into a sequence of conditional predictions, each one depending on what came before. This is one of the most beautiful and fundamental ideas in probabilistic language modeling. A whole sequence need not be predicted all at once. It can be factorized into one token at a time predictions. This is the chain rule of probability in action. Let us approach it slowly. Suppose you want to model the probability of a full sequence of tokens. That seems difficult, because the whole sequence is a large structured object. But probability theory provides a decomposition. It says that the probability of the whole ordered sequence can be written as the product of successive conditional probabilities, where each token is conditioned on the earlier ones. In plain language, to model the whole text, it is enough to model each next step given the history. This is extremely important. It means that a language model can focus on a local task that is repeated over and over, predict the next token from the previous tokens. And yet by repeating that local task, it effectively models a global object, namely the full sequence. So global language structure is built from local conditional steps. That sentence is worth repeating softly. Global language structure is built from local conditional steps. This is why autoregressive modeling works the way it does. The word autoregressive sounds technical, but the basic idea is calm and simple. The model generates one token at a time, always using what it has already produced or received as the new context for the next prediction. The future unfolds from the past, step by step. Autoregressive modeling is not an arbitrary design trick. It is a consequence of probability decomposition. Because the probability of a full sequence can be broken into conditional pieces, a model can generate language sequentially. Let us pause and reflect. A model assigns a distribution over next tokens. That distribution is conditional on the existing sequence. A whole sequence probability can be decomposed into a chain of such conditional distributions. Therefore, generation can happen one token at a time. This is the probabilistic skeleton of text generation. Now let us move into information theory, which gives us a language for speaking about uncertainty, surprise, and compression. Information theory asks questions such as these: how uncertain are we before observing the next token? How surprised are we when a particular token appears? How efficiently can a source of sequences be encoded if we know its probabilities? In language modeling, these questions are not abstract decorations. They are central. If a token is very predictable in context, then observing it carries relatively little surprise. If a token is rare or unexpected in context, then observing it carries more surprise. Surprise, in this sense, is connected to improbability. The less likely an event, the more informative its occurrence tends to be. This leads to the concept of entropy. Entropy, in this setting, is a measure of average uncertainty. If a distribution is very concentrated, with one or a few outcomes strongly favored, then the uncertainty is lower. If the distribution is spread more evenly across many plausible outcomes, the uncertainty is higher. So entropy tells us, on average, how unsure we are. When a context strongly determines what should come next, the entropy of the next token distribution may be low. When many continuations are plausible, the entropy may be higher. This idea matters because language is not uniformly predictable. Some parts of language are routine and constrained. Others are open-ended and creative. A model that captures this changing uncertainty well is doing something important. Let us say it again. Entropy is about average uncertainty. It measures how unpredictable the next step is given the current distribution. And a good language model should adapt its uncertainty to the structure of the context. There is also a deep link between prediction and compression. If you can predict a source well, you can compress it efficiently. This is one of the great insights of information theory. A sequence that is highly predictable need not be encoded with equal attention to all possibilities. More probable outcomes can be represented more economically, while rare outcomes require more descriptive effort. So language modeling is not only about prediction in the everyday sense. It is also, mathematically, about efficient coding of linguistic data. A good model reduces uncertainty and thus supports better compression. This is conceptually satisfying. To understand structure is to remove uncertainty. To remove uncertainty is to compress more efficiently. So prediction and compression are two expressions of the same underlying statistical grasp. Now this brings us naturally to the training objective called cross-entropy. Cross-entropy is a way of comparing two distributions, the true data-generating behavior, insofar as we observe it through examples, and the model's predicted distribution. When the model places high probability on the observed token, the cross-entropy is lower. When it places low probability on what actually occurs, the cross-entropy is higher. So cross-entropy penalizes bad probabilistic prediction. It is worth repeating in plain language. During training, the model repeatedly sees contexts and the correct next tokens that followed them in real data. It produces a predicted distribution over the vocabulary. Cross-entropy measures how well the distribution aligns with the actual observed continuation. If the correct continuation was assigned strong probability, the loss is smaller. If the correct continuation was treated as unlikely, the loss is larger. This is the central loss function in most large language model training. Again, the word loss is important. It is the quantity the model tries to reduce. Training is, in a basic mathematical sense, the process of adjusting parameters so that cross-entropy becomes smaller across the training data. And minimizing cross-entropy means increasing the probability assigned to correct continuations. Let us pause and reflect, because this idea is central enough to deserve stillness. The model does not directly train on vague notions such as intelligence, eloquence, or deep understanding. At the fundamental level, it trains on a precise probabilistic objective. It is rewarded, mathematically speaking, for assigning high probability to the token that actually came next in the data. From many repetitions of this process, more sophisticated behavior can emerge. But the local mathematical training signal remains astonishingly simple: predict the next token well. Cross-entropy is also connected to evaluation. If one model has low cross-entropy than another on appropriate data, it is, on average, assigning high probability to the observed continuations. That often indicates better predictive performance. And from cross-entropy we often move to a related measure called perplexity. Perplexity is an interpretable transformation of cross-entropy. It is meant to turn the average predictive uncertainty into a scale that feels more intuitive for language modeling. Roughly speaking, lower perplexity means the model is less perplexed by the data. It is less uncertain on average. It predicts better. This is the intuitive story. If a model has high perplexity, it is spreading its probability mass too broadly or assigning insufficient confidence to the actual continuation. If it has lower perplexity, it is capturing the structure of the language data more effectively. But it is very important not to overinterpret perplexity. Perplexity is useful but incomplete. That sentence deserves emphasis through repetition. Perplexity is useful but incomplete. Why incomplete? Because language competence is not exhausted by next token prediction averages. A model might have better perplexity and yet still fail in reasoning, factual consistency, planning, or long-range coherence in certain situations. Better average local prediction is powerful, but it is not identical to full cognitive depth. It is a strong indicator of statistical modeling quality, not a final philosophical verdict about understanding. So we should respect perplexity, but not worship it. Let us pause and gather what we have built. We have tokens and sequences. We have embeddings in vector spaces. We have linear algebraic transformations. We have probability distributions over next tokens. We have the chain rule allowing sequence probabilities to be decomposed into local steps. We have entropy as uncertainty, surprise as the informational weight of unlikely events, cross-entropy as the training objective, and perplexity as a transformed measure of predictive quality. Now we arrive at optimization, the mathematical process by which the model learns. A large language model begins with parameters, many parameters, often an enormous number. These parameters include matrix entries and related learned quantities. At initialization, they are not yet well adapted to language. The model must be shaped by data. How does that shaping happen? Through optimization. Training is iterative improvement. The model processes data, computes the loss, and then adjusts its parameters so that the loss will tend to decrease. This gradual movement through parameter space is one of the central dynamical processes in modern machine learning. The key concept here is the gradient. A gradient indicates how a function changes with respect to its parameters. More intuitively, it tells us the direction in parameter space in which the loss would increase most steeply. Therefore, moving in the opposite direction tends to reduce the loss. So if the loss surface is thought of as a landscape over the parameter space, the gradient points uphill, and optimization methods often move downhill. This picture is not perfect, but it is a helpful first intuition. Gradient descent is the basic idea of taking repeated steps in the direction that lowers the loss. Stochastic gradient descent and related methods use estimates of this direction based on batches of data rather than the entire dataset at once. This makes training computationally feasible at scale. It is worth repeating that optimization is how data shapes the model. The architecture provides the form of the function class. The parameters provide flexibility. But optimization is the process that actually bends the model toward the statistical structure of the training data. Without optimization, the model is just a large and trained numerical mechanism. Now, why is the gradient so useful? Because it gives local sensitivity information. It tells us, for each parameter, how a small change would affect the loss, at least approximately. Since the model may have millions or billions of parameters, this is a remarkable thing to be able to compute. Yet this is exactly what training relies on. Let us pause and reflect. The model predicts. The prediction is scored by cross-entropy. The score becomes a loss. The gradient describes how the loss depends on the parameters. The optimizer uses that gradient to make small updates. Repeating this over enormous amounts of data gradually teaches the model. Now we must ask a deeper question. How can such a huge system compute all these gradients efficiently? This brings us to backpropagation. Backpropagation is an efficient method for computing gradients in layered computational systems. It is not magic, and it is not separate from calculus. At heart, it is repeated application of the chain rule from differential calculus. That phrase matters, repeated application of the chain rule. A neural network is built as a composition of many operations. One transformation feeds into another, and that into another, and so on. The final loss depends on the final output, which depends on earlier layers, which depend on even earlier ones. So to know how the loss changes when an early parameter changes, one must propagate sensitivity backward to the chain of dependencies. This is exactly what backpropagation does. It works backward from the loss, distributing derivative information through the computational graph in an efficient way. Rather than recomputing everything separately for each parameter in a naive and impossible manner, it reuses intermediate information and applies the chain rule systematically. It is worth repeating that modern AI depends deeply on differentiation. Without efficient gradient computation, the training of large neural networks would be vastly more difficult, perhaps practically impossible at current scales. So backpropagation is not just a technical detail. It is one of the enabling mathematical ideas of the field. Now let us shift gently into the idea of neural networks as function approximators. A neural network is best understood not as a literal imitation of the brain, but as a parameterized nonlinear function. It takes an input representation and transforms it through a sequence of layers into an output. The parameters determine the precise behavior of this function, and training selects parameter values that make the function useful. The phrase function approximator is important. In mathematics, many problems can be framed as wanting a function that maps inputs to outputs in a way that matches observed structure. In language modeling, the desired function maps context to probability distributions over next tokens. The neural network provides a flexible class of such functions. Layer by layer, the representation is transformed. Early layers may capture some basic patterns. Later layers may refine and recombine them. The exact interpretation of every layer is not always simple, but the compositional structure is central. A network is a composition of learned transformations. This layered composition allows complex behavior to emerge from repeated simple steps. Each layer takes the current representation and produces a new one that is better suited for the eventual prediction task. Now, if the network consisted only of linear transformations, one after another, something disappointing would happen. The whole composition would collapse, in effect, into a single linear transformation. The expressive power would be limited. It could not capture the rich hierarchical and context-sensitive structure of language adequately. This is why nonlinearity is essential. Activation functions introduce nonlinearity into the network. Between linear transformations, a nonlinear operation is applied coordinate-wise or in some structured way. This prevents the entire network from reducing to one giant linear map. And that is crucial because language is not linearly simple. Nonlinearity gives the network expressive power. It allows the model to represent interactions, thresholds, selective amplification, and more intricate dependencies. It permits layer-by-layer transformation to build genuinely richer functions. Let us say that again slowly. Linear algebra is the main computational language. But linear transformations alone are not enough. Nonlinearity is what lets the system become truly expressive. Without it, depth would lose much of its value. With it, composition becomes powerful. This is a beautiful balance. Large language models rely heavily on linear algebra, but they are not merely linear systems. Their strength comes from the interplay of linear structure and nonlinear transformation. Now let us revisit everything once more slowly, as though we are walking back along the same path at dusk. At the entrance, we have language. Human language flowing in continuous in experience. But the model begins by discretizing it into tokens. These tokens belong to a finite vocabulary. This is a fundamentally discrete mathematical starting point. Text becomes a sequence of indexed elements. Then the tokens are embedded into vectors. This moves us from discrete symbolic identity into continuous geometry. Tokens become points in a high-dimensional space. Similarity, relation, and useful statistical structure can then be encoded through positions and directions. Once we are in vector space, linear algebra becomes the medium of computation. Vectors are transformed by matrices. Representations are mixed, projected, reoriented, and refined. Matrix multiplication becomes the recurring engine of the model's internal life. The model's goal, however, is probabilistic. It must assign a distribution to the next token conditioned on the tokens that came before. This is conditional probability in action. And by the chain rule of probability, the probability of an entire sequence can be decomposed into a product of these local conditional predictions. So full text generation becomes possible by repeated next token prediction. One step, then another, then another. Information theory then tells us how to think about uncertainty and surprise. Entropy measures average uncertainty. Rare events carry more surprise. Good prediction reduces uncertainty. Good probabilistic modeling supports efficient compression. Cross-entropy becomes the central training objective. It measures how well the model's predicted distribution matches the observed continuation. Lower cross-entropy means better probabilistic prediction. Perplexity is a transformed version that is often easier to interpret, though it should never be mistaken for a complete measure of intelligence or reasoning. Then optimization enters. The model has many parameters. Training adjusts them to reduce cross-entropy. Gradients indicate directions of change. Gradient descent and its stochastic variance use these signals to improve the model iteratively. Backpropagation computes the needed gradients efficiently by repeated application of the chain rule from calculus. Finally, the neural network itself is understood as a layered nonlinear function approximator. Linear maps transform representations, and nonlinear activations give the system the expressive power required to capture the complexity of language. Let us pause and reflect. It is remarkable that such a broad and subtle phenomenon as language modeling can be approached with this chain of ideas: discretization, geometry, linear transformation, probability, information, optimization, and composition. Each piece is mathematically natural. None alone is sufficient. Together, they create the framework in which large language models operate. Now, because the mind often benefits from repetition, let us revisit some of the central themes in a more meditative style. First, discreteness and continuity. Language for humans feels meaningful first and structured second. But for the model, structure comes first. The model does not initially perceive meaning. It receives discrete pieces. Then those pieces are mapped into continuous vector spaces. So there is a journey from discrete symbols to continuous geometry. This movement is one of the defining mathematical gestures of machine learning. Second, locality and globality. The model performs local prediction. It predicts one token at a time. And yet from these local acts, global text arises. This is a recurring pattern in mathematics, complex wholes emerging from repeated local rules. The chain rule of probability makes this rigorous. Global sequence probability is assembled from local conditional probabilities. Third, geometry and meaning. Meaning inside the model is not stored as prose definitions. It is encoded indirectly through learned geometry and transformation. Representations that matter for prediction become arranged in space. Distance, direction, and linear relation become carriers of useful structure. Geometry becomes a medium for statistical semantics. Fourth, uncertainty and learning. A model learns by reducing uncertainty about observed continuations. It becomes less surprised by the real structure of language. Cross-entropy quantifies this. Optimization drives it downward. In that sense, training is the gradual reshaping of a function so that it becomes better calibrated to the patterns of language. And fifth, simplicity beneath complexity. When one first hears about large language models, one may imagine an impossibly tangled system beyond mathematical description. But once the components are separated, many of the core ideas are classical and elegant. Finite vocabularies, vector spaces, linear maps, conditional probability, entropy, gradients, function composition. The complexity comes not from each idea individually, but from the scale and interaction of many such ideas at once. It is worth repeating that point. The mathematics behind large language models is not a single mysterious theorem. It is a large coordinated application of many familiar mathematical ideas. Now let us spend a little more time on one subtle conceptual issue. When we say that a model predicts the next token, it may sound narrow or mechanical. And in one sense it is. But if one wants to predict the next token very well across many kinds of language, one must implicitly capture many layers of structure. Grammar matters. Topic matters. Style matters. Long-range dependency matters. Common sense patterns often matter. Discourse structure matters. The model is driven by a local objective, but the data force it to internalize wider regularities in order to succeed. This does not mean it becomes human in the full sense. It means the objective is richer than it first appears. Again, local prediction can require global sensitivity. That is an important idea to carry with you. The system is not explicitly instructed in every concept. Rather, through the pressure of next token prediction across vast data, it learns internal representations that help with that task. Some of those representations align with structures we recognize as meaningful. Now let us gently revisit activation and nonlinearity, because this idea can slip away if not held carefully. A purely linear model can only form outputs that depend linearly on its inputs. Even if many linear layers are stacked, the result remains effectively linear. But natural language contains complex interactions. The effect of one token may depend on the presence of another. The relevance of a word may shift dramatically with context. A model needs flexible, context-sensitive response patterns. Nonlinearity provides this. It allows the model to bend, gate, emphasize selectively, and represent layer dependencies that cannot be captured by a single flat transformation. So although linear algebra does much of the computational work, nonlinearity gives the architecture its depth of expression. And this combination is perhaps one of the deepest recurring themes in applied mathematics. Use linear structure where it is powerful and manageable, and insert nonlinearity where reality demands richer behavior. Now let us rest again in the idea of gradients. A gradient is, in a common sense, a sensitivity map. It tells us how the loss responds to tiny changes. In a huge model, to know how to improve, one must know which parameters should increase, which should decrease, and by how much. The gradient gives the local directional information needed for that. Training is therefore not blind trial and error. It is guided movement in a vast space. Not perfect movement, not guaranteed simple movement, but informed movement. Step after step, the model is nudged toward parameter settings that better fit the data. This makes optimization feel less mysterious. The model is not taught by explicit verbal correction at the deepest level. It is taught by an error signal and a structured response to that signal. And backpropagation makes this efficient. Again, it is worth repeating that backpropagation is calculus operationalized for large compositional systems. The same chain rule one studies in analysis courses becomes a mechanism through which learning at scale becomes possible. Let us now begin to draw things together into a slow conclusion. The mathematics behind large language models begins with the choice to represent language as a sequence of discrete tokens. From there it moves into the geometry of embeddings, where discrete symbols become vectors in high-dimensional spaces. It proceeds through linear algebra, where learned matrices transform those vectors again and again. It is organized by probability because the model must assign likelihoods to continuations conditioned on context. It is justified by the chain rule, which allows sequence probability to be decomposed into local prediction. It is interpreted through information theory, where uncertainty, surprise, and compression become central ideas. It is trained by minimizing cross-entropy, evaluated in part through perplexity, and improved through optimization using gradients and backpropagation. And it is made expressive through the composition of linear maps with nonlinear activations in neural networks. All of these pieces belong together. And perhaps that is the final piece or thought to end with: a large language model is not one idea. It is a convergence of discrete mathematics and continuous mathematics, a convergence of geometry and probability, a convergence of algebra and calculus, a convergence of local rules and global behavior. If you remember only a few things, let them be these. Remember that language must first become tokens. Remember that tokens become vectors. Remember that vectors are transformed by linear algebra. Remember that the model's task is to assign probabilities to next tokens. Remember that full sequences are built from chains of conditional predictions. Remember that uncertainty can be measured, that prediction can be improved, and that cross-entropy is the central training signal. Remember that gradients tell the model how to change. Remember that backpropagation is the chain rule at work. Remember that neural networks are powerful because they are loud, learned, and nonlinear. And remember that underneath the apparent fluency of generated text lies a deep mathematical structure, patient and intricate, built from concepts that mathematics students already know in spirit, even if they have not yet seen them assembled in this modern form. Let us pause one last time and reflect. From finite vocabularies to vector spaces. From vector spaces to matrix transformations. From matrix transformations to probability distributions. From probability distributions to entropy and cross-entropy. From cross-entropy to gradients. From gradients to learning. From learning to the emergent ability to continue language coherently. That is the arc. And now, as we come to the end, let the whole picture settle softly. Large language models are machines for structured prediction over sequences. They begin with discrete symbolic input translated into continuous geometric representation, transform it through layers of learned algebraic operations, and produce probabilistic predictions shaped by optimization over massive data. Their mathematics is not accidental. It is the reason they work at all. What appears from the outside as conversation is, on the inside, a carefully organized flow of vectors, probabilities, losses, and gradients. And yet, in that hidden mathematical motion, something surprisingly human-adjacent appears, the ability to continue thought and language. Not because the machine thinks as we do, but because mathematics has given it a way to model the structure of sequences deeply enough that language can emerge from prediction. And that is where we will rest. A finite vocabulary, an ordered sequence, a point in space, a transformation, a probability, a reduction of uncertainty, a gradient-guided adjustment, a layered nonlinear function, and, from all of that, language continuing one token at a time. That is the math behind large language models. Sleep gently with that picture in mind.